Alright guys, we're going to take a look at the integral test here today, and we're also going to do an error statement with the integral test. Now the integral test is something that we can use if for some reason we're dealing with a series that's not geometric or not telescopic, or we've got the limit as n goes to infinity as 0, so I can't argue for divergence with the nth term test. What I can do is use the integral test, but this is specific only if your function that you're dealing with is continuous, positive, and decreasing. So it's got to be above the x-axis and getting closer and closer and closer to 0, which we should already know it's getting closer and closer and closer to 0, because that would be our first thing with the nth term test. If that wasn't the case, we'd already said divergent. What this says is if you have a series and you turn it into an integral and you integrate the function instead of looking at the series, if your integral converges, then so does your series. And if your integral diverges, then so does your series. One thing I want you to be careful about, though, is if you find the value of your integral to be finite, that does not mean your series converges to that number. They're almost always close, but the integral is actually going to be larger than the series. But this just says they do the same thing. So let's take a look at an example here. How about the summation from 1 to infinity of 1 over n? Now we already know that this is a p series. It's a p series with p equal to 1. So we already know that this is a p series with p equal to 1, which means that this should be divergent, because remember, p has to be larger than 1. But let's check it with the integral test. We can check by doing the integral from 1 to infinity of 1 over x dx, which of course we'll have to do this limit as b approaches infinity of the integral from 1 to b. Remember our improper integrals. And this is a pretty easy thing, integrand, to find an antiderivative of, because that's just u prime over u. So this is the natural log of x evaluated from 1 to b. And then, so that's going to be the limit as b approaches infinity of the natural log of b minus the natural log of 1. And of course the natural log of 1 is 0, so now we're going to find the limit as b goes to infinity. So I've got the natural log of infinity, and the natural log graph continues to increase, so this is a divergent integral. This integral has infinite area underneath the curve. And so since the integral diverges, so does the series. They do the same thing. Let's take a look at another example. What about, I think I showed a lot of you this in class yesterday, the summation from 1 to infinity of 1 over n squared, or 1 over n cubed, or something like that. And we saw in class that this obviously converged. We could see from the graph that it was hitting a horizontal asymptote. So this is a continuous positive decreasing function. And so what we're going to do is we're going to check the integral from 1 to infinity of 1 over x squared dx. So I'll go through my process again of doing the limit as b approaches infinity of the integral from 1 to b of 1 over x squared dx. Okay, so I'll rewrite that as x to the negative 2, because I'm going to see if this fits my very first integral formula. And this is our, our formula of the integral of u to the n du is u to the n plus 1 over n plus 1 plus c. We don't need the plus c, though, because we've got a definite integral. So that's what we have here. I've got x to a power next to its own derivative. So this antiderivative is you add 1 to the exponent and divide by that. So that's negative x to the negative 1, which I'm going to write that as negative 1 over x. And we're going from 1 to b. So let's plug in, use our fundamental theorem of calculus. We'll plug in our b, so that's negative 1 over b, and then minus plug in our 1, negative 1 over 1. So now that we've evaluated our integral, we can take the limit as b goes to infinity. Now as b goes to infinity, this first fraction goes to 0, leaving me with a finite number 1. That's the area under the curve of 1 over x squared. From 1 to infinity, it approaches 1. Now since that is a finite number, the integral converges. That means that our series also converges. And so this integral worked out to be 1. I'm curious what I said earlier, if it I'm going to have to go back and look, but I can't remember if I said the value of the integral is bigger than the value of the series, or if the series is bigger than the value of the integral. We'll investigate that and come back to that. This does not mean that this series converges to 1, because it does not. I'm pretty sure this series converges to like 1.69, I believe. But we'll take a look at it and we'll clarify that in class. But I do want to give an error statement. The error statement looks something like this. If you use the first n terms to estimate a series, the first n terms to estimate the value of the series, then obviously we are leaving off some terms, and this value is going to be less than the actual value of the series. Then we can say that the error is less than the integral from n to infinity of f of x dx. So let me show you how to use this. Let's just go back to what I was talking about before. From n equals 1 to infinity of 1 over n squared. So let's just say we want to approximate this. We're going to use, we'll plug in a 1, then we'll plug in a 2, then we'll plug in a 3. Let's go one more, and then plug in a 4. So let's just say we stop there, and this is what we're using to approximate the series. So this would be 1 plus a 4th plus a 9th plus a 16th, whatever that works out to be. Obviously, we've left off a bunch of terms, and so this value would be less than the actual sum of the series. Well, we can say that the error in this approximation is less than the integral from, I went all the way out to 4, so we're going to go from 4 to infinity of 1 over x squared dx. So let's take a look at this. And I already know that that antiderivative is negative 1 over x. And now here we're going from 4 to b, and then we were going to let b go to infinity. So we plug in our b. We get negative 1 over b minus negative 1 over 4. And so we get a value of, b goes to infinity, that first fraction goes to 0, of 1/4. The area under the curve is 1/4. But what that means is this summation, whatever that works out to be, is close to the actual value. And on top of that, we can say that the actual value of 1 over n squared, I'm going to have to extend my page here, this actual value lies somewhere in this interval from 1 plus 1/4 plus 1/9 plus 1/16. That's actually smaller than the value of this integral, of this series. And that is bounded by my approximation plus my error. This was the error. So if I take my summation and I add that error statement, I know that the actual value is in between those two numbers. So anyway, okay, I guess that's it for the integral test, and I will talk to you guys. Well, I'm going to actually talk to you today because I'm making the second period. But anyway, I'll see you guys later.